Okay, we're going to do a quick overview of Unit 1, Ancient Astronomy. I'm going to break this up into two videos. The first one being ancient astronomers and their findings, and the second video will be over celestial movements, including the celestial sphere and the seasons. So, our place in space, we're third planet from the sun, 8-planet system. We're unique in that we have lots of liquid water and life. We have a medium-sized sun. It's a yellow dwarf. It'll burn out in about 5 billion years. We live in a barred spiral galaxy known as the Milky Way. And we're a part of the Virgo supercluster. This is not the Virgo supercluster, but that's what the Milky Way is part of. This is another galaxy cluster that Hubble took pictures of. And this picture is the Hubble Deep Field, one of the most famous astronomical pictures ever. Let's talk about what astronomy is useful for in ancient times. Numerous things, including navigation. On the sea, obviously, this is huge. On the land, they also used navigation by the stars with things like the astrolabe. On the sea, they used the sextant, at least in more recent years. But ancient celestial navigation is extremely ancient. It's just based off of the stars, minus the tools. Timing, as far as when the sun was going to rise, when it was going to, set, when the lunar month was. These are all important timekeeper devices for the ancients. And also planting and harvesting crops, which could be the difference in living or dying for your whole tribe. We're going to look at a couple of the more famous astronomical tools, I would say. At least we suspect they're astronomical tools. There's no real evidence, especially for Stonehenge, as there's not any written history about it. It's prehistory. Located in England, constructed over about 1,700 years. Believed to be an astronomical calendar, as it is aligns with multiple things. In North America, the most famous observatory in ancient times was the Caracol Observatory, built by the Mayans in 1000 AD. Has several different windows that align with astronomical events, such as solstices, equinoxes, and also the rise and fall of Venus, the Venus phases. I'm sorry, the Venus period of revolution, which the Mayans, for some reason, seem to think was very important. And it's probably because Venus is so bright and easily visible. Greeks in ancient time, lots of contributions to astronomy. The Pythagorean theorem, for instance, had geometry and trigonometry was first established by them. The Pythagorean theorem is very influential in measuring distances to nearby celestial objects, and this was used in ancient times, at least for early estimates. Aristotle, first person to, I hate to say first person, but he concluded that the Earth is round, and he based that on the fact that the moon and the sun appeared like spheres or circles in the sky, if you will. He said if these things are round, then the Earth is probably round. Columbus is not the first person to believe that. Chinese astronomers are well-known documenters, and they kept very accurate records of what they considered to be weird things astronomically. Eclipses, comets. One of the most famous things they recorded was the 1054 supernova, which left us with the Crab Nebula, which is this little bad boy over here. Middle Eastern astronomy was very huge in ancient times. Probably the most used in the Middle East as far as navigation especially. They developed the astrolabe, which is this little guy up here. Showed it to you in class. It's basically a primitive GPS. This is also an astrolabe. And lots of astronomical terms go back to the Middle East. Azimuth, zenith, Betelgeuse, Vega. There are certainly others. Those are just examples. Erastusines. He's Egyptian. He was a librarian in Alexandria at the very famous Library of Alexandria of antiquity. He predicted the Earth as a sphere and did an experiment that proved the Earth as a sphere. He actually didn't do the experiment. He paid somebody to walk from Alexandria to Siam to measure this distance here. Then he measured the angle difference in Alexandria of a stick in the ground, or who knows, an obelisk or something. And then at the exact same time, roughly, as the sun was overhead in Siam, and it shone all the way down to the very bottom of the well. This gave him a percentage that from this distance that he compared that distance to 360 and calculated the circumference of the Earth within about a 1% accuracy. So geocentric universe is the idea that the Earth is the center of the universe. It certainly looks like that. You know, just standing on the planet and you see things moving around you all the time. Doesn't feel like the Earth's moving. So as crazy as the theory as we think that is now, that's very easy to understand why they would believe that in ancient times. In fact, it was taught for over 1,600 years. Ptolemy, another Greek dude, not Leonidas, first proposed the Earth as the center of the solar system, believed it because it's what it appears. Again, we see the sun setting and rising, we see the moon going around, and it's hard to understand how the Earth could be moving. Geocentric model had a problem with retrograde motion, though. Retrograde motion is the idea that a planet seemingly slows down and then it starts going backwards for a period of time. Then it starts going in the regular or prograde direction again. This is actually shots of Mars over time, and as it's kind of going this way, this way, this way, this way, you can notice that this is from one night to the next night, the gap here starts to shorten, which indicates it's slowing down. And then, in fact, it actually goes backwards, and then it starts to go prograde again, which is here. So this is very confusing to the ancients. We understand why that is currently, but Ptolemy, who came up with the geocentric model, came up with an elaborate system to try to explain retrograde motion. And this elaborate system was the epicycle and deferent system, where he said that each planet goes in a large orbit called the deferent, which is in this case is this orange line here. But then it also goes in its own little mini orbit within its orbit called an epicycle. Now this kind of semi-made sense as far as why it would look like something would go backwards. If you look at it here, as it's going within its orbit here, it happens to look to loop around here within its orbit, going around our orbit here. So this is widely believed for a long time. Doesn't exactly explain retrograde motion, especially with some of the other planets. With Mars, it kind of worked decently, but some of the other planets, it gets wonkadoo. You can look at Venus here and what's going on here, and Jupiter out here that's very inconsistent. Along came this guy, Nicholas Copernicus. Not the first person to propose the sun was the center, but Aristarchus was the first. Aristarchus also made his 500-star catalog. Wasn't widely accepted, kind of forgotten almost, a couple thousand years later almost. Copernicus, who was a monk, figured out that the sun was really the center of the solar system, not the Earth. This proved how retrograde motion worked, and I'll get to that in a second. But it places planets in circular orbits around the sun, which is incorrect, but for the most part, I mean, obviously it's a monumental accomplishment. Here you can kind of see a background, or I'm sorry, an example of what he shows. This shows the planets in exact circles, which is incorrect. But it does fix retrograde motion, and the reason it fixed retrograde motion is because it's hard to look at this here, but if you're on Earth, you look up here, there's Mars at this position. When Earth's here, Mars is at this position, right? You have to look at it from here to here, but in the night sky it looks like this. Third position, it's here. So it's still going prograde. Fourth position, it's here. Fifth position, it's here. The sixth position is where it gets funky. The sixth position is where it actually appears to go backwards. And what's happening is Earth is actually passing Mars. So 6 is where it looks like it went backwards from 5. And then if you look at position 7, it is backwards relative to Earth. But then position 8, it started going prograde again, which means it's going the correct way. This is huge. It explained retrograde motion. Then came Galileo. Lived in Florence, Italy. Close to Rome, had a lot of influence, money. He's very intelligent, so this goes a long way in ancient times. Known as the father of experimentation, first person to experiment with inertia and gravity. Newton goes on later to kind of explain these things better, but Galileo definitely had it in the right track. But astronomically, he's the first person to study astronomy using a telescope. He's not the inventor of the telescope, but he's oftentimes accredited with that, but he's not. He made modifications to it, made it better for that. Actually got the town of Florence to buy telescopes to foresee having naval invasions come into the port and take over, actually for Venice, sorry, not Florence, for naval invasions as kind of a protection. He was argued that if he could see the enemy coming way before they were here, then they'd have time to prepare. But he actually wanted it for astronomical purposes and just kind of got the government to pay for it, which is pretty smart. It's a basic two-lens model with a slide adjust. Allowed him to see things about 10 times magnification, which at that time is, ridiculously better than the naked eye. These are some sketches of Galileo's. These are some of his major findings. He found the 4 Galilean moons, which are the 4 largest moons of Jupiter. This helps to support heliocentricity because the moons were orbiting around these planets here, and it kind of outlined the idea that Earth wasn't the center, right? In that case, Jupiter was the center with the moons going around it. Realized that Venus had phases. This is a huge thing for heliocentricity because if if the universe is geocentric, then we would not see all the phases of Venus. These would all be, fairly darkened shades because there would be no fully lit surface of the planet, which in this case is the sun-centered model, the heliocentric model. We do see full phases of Venus. We would not see a full phase of Venus if it were geocentric. So if you look at kind of a list, these are the Galilean moons. Planets are circles or Earth-like. Venus has phases. The moon is not smooth. This was a thought for a long time. The world was kind of, or that the moon was a perfect celestial body, but it was not smooth. Had craters, has mountains, very uneven. Discovered the sun had sunspots. Noticed that they were moving, and therefore the sun was rotating. He did go blind from studying the sun. He did go blind. I hate to say he went blind going by studying the sun, but probably had a lot to do with it. Then comes along a guy named Tycho Brahe. He's hired by a Denmark king to have as the official mathematician which used to be a position in antiquity because you wanted to have really smart people around you. It's theorized that he died at dinner via a bladder explosion, but it's now believed that he died from poisoning, mercury poisoning, which some people even pointed to Kepler for, who is his apprentice. Brahe had a rather large telescope that was very different than Galileo's type of telescope. It was really just more about plotting data for accurate planetary orbits. It wasn't really for looking at anything better. It was just a data plotting device. He hires Kepler, who is a mathematician. He's not an astronomer. He's a numbers guy. He comes in, starts basically crunching all the data that Brahe had, and after Brahe died, he got his hands on all this data and came up with 3 laws of planetary motion. First law of motion is that the path of each planet around the sun is an ellipse, not a circle. Remember, Copernicus said it was a circle. They're not circles, but they are in fact ellipses, which is in more of an oval shape or a squash circle with 2 foci. So one foci is over here, imaginary, and the other's in the center of the sun, and then the planet here. So here's a circle with an eccentricity of 0. Here's a ever-increasing eccentricity. This is probably about a 0.4, 0.5. And then eventually, if you keep increasing the eccentricity, it will go completely to 1, which would be a straight line. The oval flattens out. Second law of planetary motion is that each planet revolves so that an imaginary line sweeps over equal areas and equal intervals. So this said that this amount of area here is the same amount of area as this, and you have to think about area, not distance or anything. So 1 month out here, the planet only travels from here to here. In 1 month here, it travels from here to here. So the distance is greater in the same amount of time. That says that as planets get closer to the sun, they speed up. And as they get further away from the sun, they slow down. This certainly is the way that planets orbit. This is very eccentric. We don't have any planet in our solar system that's like this. This would have a significant slowdown and then a significant speed up. We don't have anything that extreme. Mercury's is the most eccentric, although Pluto's is fairly eccentric too, but and it's nothing like this, not that crazy. Kepler's third law says that a planet's orbital period squared is equal to the mean solar distance cubed. Now, what does that really mean? Well, you can take how long it takes to make one complete revolution, square that, and then that'll be the cube root of the distance of the planet, which basically tells you if you can calculate how long it takes to go around the sun one time, you can find out how far away it is, because they're proportional. It's a good example of this. Mercury has a distance of 0.39 AUs, which should go back to that. It gives us the astronomical unit, which is the average distance between the Earth and the sun. Kepler set the astronomical unit of the Earth as 1, just making it easier to kind of base it off of Earth. Anything less than 1 is closer to the sun than Earth, and anything over is more than 1. So you look at Mercury, it's 0.39 AU, so it's much closer. It has an orbital period of 0.24 Earth years. So it's really, really rapidly orbits the sun. Pluto, on the other hand, very far distance, 39.44 AUs. It's way out there. Has an orbital period of 247 years. Sir Isaac Newton lived in England, was a professor at Cambridge. He's known as the father of physics. He created calculus to explain physics, Wrote a very famous scientific book known as the Principia. It was very familiar laws, right? Newton's first, second, and third law of motion. Object at rest remains at rest, and object in motion remains in motion unless acted on by an outside force. This is very applicable to astronomy in numerous ways, including orbits. Newton's second law, F equals m times a. Third law, for every action there's an equal and opposite reaction. So these are pretty basic. You probably learn this forever. He also went over the law of universal gravitation. I'm trying to find that, but introduced the law of universal gravitation and the inverse square law of gravity. He said that anything with mass shares an attractive force to anything else that has mass. The smaller the mass, the weaker the force. Further apart, weaker the force. So this is the law of gravitation. This led to the inverse square law of gravity, right? This is very famous universal law of gravitation formula. Inverse square law of gravity states that as distance increases from a massive body, gravitational influence decreases. It's pretty basic. The further you get away from something that has mass, the less gravitational influence it will have on you. This graph kind of shows that. So distance 1, force is 1. Distance 2, it is a quarter of the gravitational force. So hence the square law. 2 squared, 1/4. So the inverse square law reinforces Kepler's second law of planetary motion. Planets close to the sun should move faster. Planets further away should move slower. But it also led to orbits, the idea behind orbits. Orbits are a combination of two different forces, a planet's inertia and the pull of gravity from the sun. So you have the pull of gravity here. The planet wants to go this way. A combination of those two forces makes the planet go this way in a circular path. Near circular. Escape velocity is the speed required to escape any massive object. Earth's escape velocity is about 14,000 miles per hour. Every object has its escape velocity. A human has an escape velocity if you're in space. And the human's escape velocity is ridiculously small. Because the human's mass is ridiculously small. So, another example of something that has a lot of mass is a black hole. A black hole has theoretically infinite mass. So it therefore has infinite density, and it therefore is basically impossible to escape. So that's why they are called black holes. Any light that happens to go into a black hole will never be able to, escape, because the escape speed is faster than the speed of light. And the moon is falling is Newton's idea behind, which led him to the orbit idea. It's believed that probably most of his major theories about gravity came about by moon observations and had very little to nothing to do with an apple falling on his head. So he said, why doesn't the moon just keep going out here? And he said there must be some kind of force holding it to it, and that force was the Earth's gravity. So he said inertia plus gravity makes an orbit. So the moon wants to go out here, Earth's like, I don't think so. So if its direction is constantly changing, then its velocity is constantly changing. So the moon is constantly accelerating, which does not by definition mean that it's going faster. It just simply means that its velocity is changing because its direction is changing. And that will be it for this video. The second video will be over the celestial movements.